Let's try and wrap our heads a little more about what it means for a circuit to behave at resonance. The generator can drive a current at any frequency. We'll call that omega d. So when we say that the current that oscillates in this circuit is equal to some current amplitude multiplied by cosine of omega t, this cosine is whatever driving frequency your generator is set at. Now, regardless of what type of generator you select, and whether you call the peak voltage capital V or you call the peak voltage script E for EMF is up to you. Regardless of the driving frequency, once a particular value of capacitance and inductance is fixed in the circuit, there's no changing the frequency at which the circuit would achieve resonance. The resonant frequency is equal to 1 over the square root of the inductance multiplied by the capacitance. So let's take a look at our phasor diagrams. We're going to do 3 cases. We'll say in the middle, if driving frequency is equal to resonant frequency, what does the phasor diagram look like? In the first case, what if the driving frequency is greater than the resonant frequency? So in the last case of our phasor diagram, we'll show what it looks like if the driving frequency is something less than the resonant frequency. For some reason, I've chosen to put the phasor that represents the current or the voltage across the resistor at the same position in the first quadrant every time. I don't know why I've been electing to do that. That phasor can point into any quadrant. Let's say that at some instant in time, the voltage across the resistor is approaching its maximum negative value. So that phasor would be somewhere in the second quadrant. So let's label that V subscript R. So if I want to show the voltage across the inductor, well, voltage across the inductor, Eli the Iceman, the voltage across the inductor always leads the voltage across the resistor by 90 degrees. And the voltage across the capacitor lags the current or lags the voltage across the resistor by 90. Notice that I've made the magnitude of the voltage across the capacitor less than the magnitude of the voltage across the inductor. Well, that's what happens when the frequency is greater than the resonant frequency. After all, the voltage across the inductor should be equal to the current amplitude multiplied by the inductive reactance. And inductive reactance is equal to the driving frequency multiplied by the inductance. So as the driving frequency increases, the inductive reactance increases, so the voltage across the inductor increases. Okay, so the net result of this, we can draw in a vector that represents the difference between the voltage across the inductor and the voltage across the capacitor. So the net effect is those have canceled and we're left with the combination of the two. So that gives us, based on the parallelogram method for vector addition, a total voltage around the circuit that has a phase angle that leads the voltage across the resistor. Let me skip over the resonant condition and remind you one more time with the phasor diagram. This time, just for the heck of it, let's imagine that the voltage across the resistor has already reached its most negative value and is starting to become less and less negative and approaching towards 0. So we always imagine that our phasors are rotating counterclockwise. So we'll say, for example, that represents the maximum voltage across the resistor. So the voltage across the inductor always leads by 90 degrees, so it's rotated further ahead. And the voltage across the capacitor always lags by 90 degrees. Now this time, I've made the voltage across the capacitor greater in magnitude than the voltage across the inductor. The reason for that is voltage across the capacitor is equal to capacitive reactance multiplied by current amplitude, but capacitive reactance is equal to 1 over the driving frequency multiplied by the capacitance. So as the driving frequency gets lower and lower, the capacitive reactance increases, and therefore the voltage across the capacitor increases. So we can draw in a vector that represents the difference between the two. So here's voltage across the capacitor minus voltage across the inductor. And once again, by the parallelogram method, now we have a net value. And we can see in this case, the phase angle shows that the voltage lags the current. Okay, so you can predict, if you don't already know, what happens at resonance. At resonance, the voltage across the resistor, the voltage across the inductor, and the voltage across the capacitor might look something like this. The key feature is that the voltage across the inductor and the voltage across the capacitor are now equal in magnitude, so they cancel each other out, and so all you're left with as the net amount of voltage is the voltage across the resistor, meaning they're one and the same. The overall max EMF of the generator matches the maximum voltage across the resistor, and they're perfectly in phase with one another. So let's see if we can highlight with another graph this relationship, that inductive reactance is directly related to driving frequency, whereas capacitive reactance is inversely proportional to driving frequency. So we can make a graph that shows what happens as the driving frequency increases from 0 up to some value to both the inductive reactance and the capacitive reactance. So if the driving frequency is 0, then you have 0 inductive reactance, and the higher and higher it gets, the greater and greater, in a linear fashion, the inductive reactance becomes. Now, this is a curious one. At 0 frequency, what's the capacitive reactance? Well, now we have division by 0, so in other words, it becomes infinite. There's infinite capacitive reactance at 0 driving frequency. And as the driving frequency gets greater and greater, it comes down. So this is really just an inverse curve. So there's a particular point where the two have the same value. At this point, the inductive reactance and the capacitive reactance would be equal. And so if we mark that point on this graph, this is the resonant frequency. So this would mean that omega times L would have to equal 1 over omega times C. Let's multiply both sides by omega. Okay, so it cancels here. Let's divide both sides by inductance. So we're left with omega squared is 1 over LC. So this is why we say the resonant frequency is equal to the square root of 1 over LC, as we stated at the outset of this video lesson. How do we calculate the overall impedance in the circuit? So remind you the formula: resistance squared plus the difference between the inductive reactance and the capacitive reactance quantity squared. Okay, so let's see now. Phase angle. Gosh, what would happen if the driving frequency wasn't just a little bit greater than the resonant frequency? What if our driving frequency was ridiculously larger than the resonant frequency? Well, you can see here, if we extend this graph, basically as the driving frequency approaches infinity, then the inductive reactance approaches infinity, and you'd get to the point where the voltage across the inductor would so overshadow the other components' voltages that for all practical purposes, the overall EMF would almost match the voltage across the inductor, and your phase angle would then approach something close to positive 90 degrees. So that's the greatest phase angle you could ever get, is positive 90 degrees. Likewise, if the frequency tends towards 0, then this equation, or this graph, shows us that as the driving frequency goes towards 0, then the capacitive reactance approaches an infinite value. And so that would change this Phasor diagram. It's the voltage across the capacitor would become so much larger than any of the other voltages that it would cause the overall EMF to no longer line up and be only slightly out of phase with the current. It would be almost in phase with the voltage across the capacitor, and so you would have a phase angle in this case that approaches negative 90 degrees. So did you catch all that? When the driving frequency is at 0, then almost all the voltage, right, we hook up voltmeters across all three of our circuit components. If the driving frequency is nearly 0, then the voltage across the capacitor is almost equal to the full EMF, and the voltage across the resistor is almost 0, and the voltage across the inductor is almost 0. And in that case, the impedance, or the overall impedance, is nearly, it's largely favored toward the capacitive reactance, and the capacitive reactance itself would tend toward an infinite value, and the phase angle would go toward negative 90 degrees, and in this case the circuit is behaving very capacitively. So you have a phase angle of negative 90 degrees at most and positive 90 degrees at the greatest, and the phase angle is negative 90 degrees when the driving frequency is 0. The phase angle is 90 degrees when the driving frequency approaches infinity, and the phase angle is 0 right at a driving frequency that matches the resonant frequency. So we have a graph that looks something like this. And we'll wrap this up with a graph of current amplitude versus driving frequency. So let's see, if we drive the circuit at the resonant frequency, let me write this again, impedance is the square root of resistance squared plus inductive reactance minus capacitive reactance quantity squared. So if the driving frequency equals the resonant frequency, then the inductive reactance equals the capacitive reactance, and so this quantity here goes to 0, and in that case the impedance is just equal to the square root of the resistance squared, or in other words, the impedance is just the resistance of the circuit. But if it's a case where the driving frequency is greater than the resonant frequency, then the inductive reactance is greater than the capacitive reactance, and this term in the equation is something other than 0, which means the impedance is now greater than the resistance by itself. And likewise, if the capacitive reactance is, you get a capacitive reactance that's greater than the inductive reactance in the case when the driving frequency is less than the resonant frequency. But because this term is squared, it doesn't make a difference. If this value is negative, once we square it, that becomes positive. And so no matter what, if the driving frequency is anything other than the resonant frequency, the impedance is always greater than the resistance. And current amplitude is equal to the maximum voltage divided by the impedance. So basically what we're saying is you get the greatest possible value for current amplitude if the impedance is equal to the resistance, and that only occurs when we drive the circuit at the resonant frequency. So the current amplitude is going to have its greatest value when the driving frequency is the resonant frequency. If the driving frequency is 0, then the capacitive reactance goes toward an infinite value, and if the impedance goes toward an infinite value, then the current amplitude is going to go towards 0. So we expect to have a curve that starts at 0 for the current amplitude and reaches a maximum value when the driving frequency is the resonant frequency. And then as the frequency goes higher, it starts to come back down. Now, this is not a symmetrical curve. The reason is there's a finite amount of values between 0 and resonant frequency, but from there on, there's no limit to the upper value of the driving frequency. It can tend toward an infinite value. So this graph is not symmetrical about the resonant frequency. And so the interesting result of all this is that resonant frequency is independent of the resistance value. It's not independent of the inductance or the capacitance. In fact, the equation tells us that the resonant frequency is the square root of 1 over the product of the inductance and the capacitance, but it's totally independent of the amount of resistance. So what would happen if I kept the value of inductance and capacitance the same and changed the value of resistance? Then our graph would always have its peak value for current amplitude at the resonant frequency. It's just with a larger value of R, we would have a smaller overall current amplitude. And with a smaller value of resistance, we'd have a greater overall current amplitude. So let's label all these, we'll say, with small resistance and with large resistance, and then of course this curve would be with some intermediate value of resistance. Okay, so hopefully that gives you a little better insight of what we mean when we say we can drive an LRC series circuit at resonance frequencies.